do this right away. So for those who came in later, this is the scenario. This is just problem 6 from homework number 4. You have two loops, one big and one small, separated by a distance x that can change. The lower loop, which is bigger, has a clockwise current in it of I, and we know that the separation between these two loops is much greater than the radius of the big loop. And so that'll be important. So we know that x is increasing at some dx dt equal to v. Some dx dt equal to v. So it asks, what is originally the flux of the upper loop as a function of x? So we can already write down a general expression for flux, right? We know that magnetic flux is always equal to, well, what is it equal to? It's equal to b dot dA, always. Now in this case, if the upper loop, right, it's not deforming at all, it's not changing in area, it's not rotating, it's just moving up. So since the magnetic field that this lower loop produces is always, it's not constant, it's going to be a function of separation, most likely. But what will happen is it will still be in the same direction, right? A is not changing. So really, this is just equal to B times A. That's it. That's it. So we know what the area of this upper loop is already. This is just, so this is B to the lower loop multiplied by pi r squared, because that's just the area of the upper loop. Simple enough so far. Okay, but what's B of the lower loop? So we did this in an earlier problem, right? If you just have a loop of current and you're trying to find the magnetic field at some distance z, right, away from the center, this is equal to mu naught I believe, over 2 pi, and then we have r squared over z squared plus r squared to the 3/2. Correct me if I'm wrong, but I believe that is the expression. So we've already done the work to show that this is the magnetic field of a current loop. And this is, yeah, so this is indeed the case. This is indeed the case. Sorry, there's one thing. There's no pi. No pi. Just mu naught I over 2. There we go. Right. So, yeah, there's no pi. So this is the magnetic field due to a current loop. Now, we need to start making some approximations here, right? Because we are told that, in this case, x is much greater than r. And with the expression that we wrote up top here, x is equal to z in this case. So when z is much greater than r, what does this expression reduce to, right? So mu naught I over 2 r squared over, so this is basically, I'll do this. So whenever you have these types of approximations, you always want to rewrite this in terms of a ratio. So if z is much greater than r, right, then z, or if z is much greater than r, then r over z is much less than 1, right? I just rewrote this inequality in terms of a ratio. So in that case, we can say that this expression 1 plus r over z is essentially just 1. That's why we always write it like that. Reason being, if I take this, right, I want to factor out z, because if I do that, if I factor out z outside of this expression, then I'll be left with r over z over here and a 1. And then I can use this to sort of approximate that as equal to 1. That's how you properly do these types of approximations in physics problems. So I have z squared 1 plus r squared over z squared. So this is definitely the case for sure. If r over z is much less than 1, then r squared over z squared is definitely much less than 1 to the 3 halves. And so I'm left with mu naught I over 2 r squared. And on the bottom side, we have z squared to the 3 halves. So that's just z cubed and 1 plus r squared over z squared to the 3 halves. But we know that because of the approximation, this essentially cancels out. It's essentially 0. So we're just left with mu naught I r squared over 2z cubed. And that's it. That's it. When z is much greater than r. Okay, so now finally putting it all together, we just want to know the flux, right? So this is just equal to b dot a, which is equal to mu naught I r squared over 2z cubed multiplied by pi little r squared. There we go. That's the flux as a function of the separation. So I really have z, but the problem calls it x, so this is really x, right? You just replace z with x here. Yeah. Okay, so that's part A of the problem. Part B asks, okay, now determine the magnitude of the induced EMF in the smaller loop. So this is a fairly simple problem. We know that from Faraday's law. This is just minus n, change in flux, over change in time. So since the number of loops in this turn, the number of turns in this loop is just 1, right? This is equal to minus delta B over delta T. And since we know that this is essentially a continuous change in the separation, we can really just go ahead and call this minus D dt. That's really what this is, right? We're looking at an instantaneous change in the flux. So we know that d flux is equal to mu naught, or d over dt. Right, so just a little bit of calculus here. Mu naught I r squared pi little r squared all over 2x cubed. So all of these things, say for x is constant in time, right? The current is not changing. Mu naught doesn't change, that's just a constant. Big R and little r don't change, right? It's the radii of the loops. So these can all be brought out. So mu naught pi I r squared, little r squared, over 2. And we have d over dt, 1 over x cubed. Now, recalling from calculus, I'm just going to call this some constant c naught, right? Because I don't want to have to keep writing that. So we know from calculus that d over dt 1 over x cubed is equal to d over dt of x to the minus 3, right? This doesn't change. I'm just rewriting it in a different notation. So this is c naught multiplied by minus 3x to the minus 4 dx dt. This is just the chain rule that we use here, the chain rule for derivatives, right? So looking at this, we have minus 3 c naught over x to the 4th dx dt, but it defines dx dt as some constant v here. So we can just call this v. And so we see that the instantaneous EMF as a function of distance, right? So the EMF as a function of distance is now equal to minus 3 mu naught I pi r squared, little r squared, over 2 v and 1 over x to the 4th. It seems a little complicated of an expression, but it's very straightforward, right? Just a lot of pieces to keep together. Yeah, and that's exactly it. Okay, so that is the EMF as a function of separation. Now part C asks, what is the direction of the current in the small loop? Is current in small loop direction of current? Because we don't know the resistance of the loop, so we can't really figure out the instantaneous current, but we can figure out the direction, right, via Lenz's law. So what does Lenz's law tell us? Lenz's law means that the current should always be such that it opposes the original change in flux, right? So what is the original flux on this guy? Well, let's originally draw it out, right? So we see here that really the flux is pointing upwards originally, right? So it's some number. That number exactly is mu naught I r squared pi little r squared over 2x cubed, right? It's this mess over here. That was the original flux, and it's pointing upwards. But as you move farther and farther away, what's happening? That flux decreases, right? So the original flux that's pointing upwards decreases. So Lenz's law says that the upper loop wants to oppose that, meaning that it wants to create its own flux, its own magnetic field pointing upwards. And so the only way to do that is to have a current flowing counterclockwise. So this is counterclockwise. I know Lenz's law can seem a little confusing. Does anybody have any questions regarding why this is counterclockwise? If not, that's okay. I can assume that you do understand, but if you don't, please don't hesitate to ask. Okay, so allow me to repeat. So the original flux, I guess I can write it. So original flux before change was pointing upwards. Right? So as x increases, flux remains pointing up, right? Because the direction of the magnetic field doesn't change with the distance. It's just the magnitude. But flux, so the magnitude decreases. So Lenz's law says induced B from small loop will oppose this change. Meaning that B induced will point up. And this is only possible with a counterclockwise current, right? Because look at the loop, right? It's only possible if it were counterclockwise. That if, you know, via the right-hand rule, if you had a counterclockwise current, then the magnetic field from that lower loop would be pointing up. And based off of the reasoning which I just wrote down, that is why it has to be counterclockwise. So it's all Lenz's law, right? It's all Lenz's law. Any questions on the explanation? Not, you know, I'll leave this, and this will be in your notes for, this will once again be in the Google Drive folder. Okay. So that's one problem. We have a few more to go through. I want to start going into inductors. Have you guys learned about inductors yet in your class? In inductance, so LC circuits, RLC circuits. Because we do have 3 problems with inductors in it. Okay, so I'll start covering that because I haven't covered that with you guys yet. So this first problem that I'm going to cover is problem number 8 with inductors. Homework 4. So you have a circuit here. It's the point X. Here's a resistor with the current I flowing through it. Here's the point Y. Now you have an inductor. And that's it. So there's some inductance L here. And this is the point C. And so it tells us that the current as a function of time is just A plus B T, where A and B are constants with their own appropriate units. The resistances R and the inductance is L. So now it's asking, what is the battery EMF as a function of time? So this is just understanding how Faraday's law applies to inductors, right? So the basic point of an inductor is essentially just a coil of wire. And so when current flows through this coil of wire, if it's a constant current, it's all fine and dandy. It produces a magnetic field, according to the right-hand rule, and we're golden. There's no particular problem here. But what happens when that current starts to change, right, in a battery? Say you're charging a capacitor, right? That current is not going to stay the same forever. So when the current starts to begin to change, what's going to happen? The magnetic field that solenoid was producing, that coil was producing, will now change. And it doesn't like that. So it will essentially try to produce its own EMF to resist that change in current. And this is known as usually EL, and it's going to point that way if the EMF is pointing this way originally. So this is known in many cases as a back EMF because it's opposing any change. We know that, so since the current is increasing, the direction of the EMF for the inductor is going to be this way, right? Because it's trying to oppose that increase in current. If it were decreasing, then the EMF would be this way. So we know that, just by applying the loop rule, you can pick, I guess that's why they have X, Y, and Z. You can pick any point and apply the loop rule. I'm just going to start from the point Z and then work clockwise. So we have E minus I of T R, and then minus EL. And so Faraday's law tells us another expression for the back EMF of an inductor. And if you don't remember this expression, it is just equal to, really, I guess I should put it like this. So it's plus EL. It's really like this, minus L d I dt. The minus sign really belongs in this expression, where L is the inductance of the solenoid, and that's measured in henries. Okay, so writing out this expression, this is equal to 0 because we're applying Kirchhoff's loop rule. And so we have epsilon, or E, minus A plus B T R plus, or really there's a minus sign now, because now I'm applying the minus sign, minus L di dt, right? Di dt in this case is just the derivative of this function up here, which is just b. It's just a constant b. So minus L b equals 0. So we just move everything over and we get that E as a function of time is just L b plus R A plus b t. So it still changes as a, it's still increasing as a function of time. And now it asks, so that's part A. Part B is also fairly simple. It asks, what's the rate of change of the battery EMF? So the change is just d dt. And once again, you're just taking another derivative with respect to time. And so we see here that the only thing that is in front of a variable t is r and b. So this is just r, b. It's a constant change in the EMF. It's a constant change in the EMF. So this question is fairly simple. It's introducing you to the concepts of, back EMF and how inductors do this. So now let's get a little more complicated. Let's get just a little more complicated. Let's talk about oscillators. I'm sure you've covered that at some point. So oscillators. So this is if you have, I'm sure if you've seen an LC circuit. Has Dr. Greenbaum shown you an LC circuit? Has he gone over the relevant equations of an LC circuit? You can say yes, you can say no, you can say I don't know if you weren't paying attention. But just so I know. Wonderful. Okay, so there's an LC circuit. There's also RLC circuits. So there's R, L, C. Okay, so let's talk about an LC circuit first really quick. In an LC circuit, what is happening? So assume for C, there is charge Q naught in the very beginning. So it's fully charged. You close the switch and you let it discharge. But what's going to happen? You're starting to ramp up the current, or you have a really high current in the beginning, right? And remembering how capacitors discharge, right? The current falls. Yes, that's exactly it, right? So, as you close the switch, the capacitor is going to have a really high current in the beginning, but then that current is going to try and decrease. It's going to try and decrease, but the inductor doesn't like that because you're changing the current on it. So it's going to produce its own EMF to try and resist that. So essentially what's going to happen is you're going to have this flip-flop. It's going to act like a sine function or a cosine function. The charge is going to flip-flop back and forth. You can also think about this in terms of an energy prospect, right? So you know that in a we are back. My apologies. So you know that for a capacitor, there's energy stored in that capacitor, right? This you've probably seen as 1/2 CV squared, where V is the voltage on that across that capacitor. Now we can also write this in terms of the amount of charge, right? Because this is 1/2 C, and we know that Q is equal to CV. So this is Q over C squared. So this is equal to Q squared over 2C. Right, that's the energy stored in a capacitor. That's the energy stored in a capacitor. Likewise, the energy stored in the inductor is always equal to 1/2 Li squared. And this is 1/2 L dQ dt squared, right? And so conservation of energy tells us that UL plus UC is a constant, right? Because the energies, we're assuming that there's no loss here. We're assuming that there's no damping, no friction, no resistor in just an LC circuit. So this is some constant, right? We'll call it U. And we know that du dt is equal to 0. So we can say that dul dt plus duc dt. This makes a differential equation, right? So this gives us an equation of, I'm just writing it really quick. I'm not going to show you how to solve the differential equation just yet. I'll just tell you the solutions. So in this case, we have dul dt. So this is the derivative of this with respect to time. So that gives me a 2 brought down from the chain rule mixed with the 1/2. That cancels out. So we have L dq dt and then d squared q over dt squared plus On the other side, for this guy, the derivative with respect to time is 2q dq dt all over 2c. So that those 2's also cancel out. Wonderful. So this is equal to 0. We see here we have a dq dt on both sides. And since the other side is 0, that can just cancel out. So we're left with L d squared q dt squared plus q over c. So if I want to move stuff over to make it a proper differential equation, I have d squared q over dt squared is equal to minus q over LC. Right, so I just moved the q over to the other side, and then I divided both sides by L. And I can call this something else. I'll call this minus omega naught squared q. And so this is a sort of like a classic differential equation that you should have seen many times by now. And even if you don't know how to solve it, you should recognize that, right, there is a family of functions. There's a class of functions where if you take the second derivative of it, it gives you the same function with a minus sign. The only functions that can do that are sines and cosines. The only functions that do that are sines and cosines or exponentials. But for this case, we're just going to talk about sines and cosines. So the solution of this is, because of our initial conditions, this is essentially q naught cosine of omega naught t plus some phase angle. That doesn't particularly matter. But we see here now there's a frequency, a resonant frequency for the circuit. Excuse me. Not sure who that was. So there's a resonant frequency for the circuit. And this is just 1 over square root of LC. So you're going to be seeing this a lot. Resonant. So this is a pure resonant frequency for a circuit. Pure resonant frequency. Okay, but the problem here now is that this is for perfect oscillations, right? So the energy is, constantly moving back and forth. The charge is moving constantly back and forth. But this isn't practically the case. There's always some damping. In 111, have you guys discussed damped oscillations at all? Like, do you remember if a spring was like moving back and forth, but there was some damping and eventually it would settle back? Does this sound familiar to you at all? Have you covered this at any point? This is a question I'm posing to you guys. No, when friction is present. Yeah, so there's usually some like damping. So, how a spring, because of Hooke's law, will constantly oscillate back and forth from the equilibrium forever. But if you finally include some friction or damping, eventually it's going to lose that energy and then it's going to stop oscillating altogether, right? That's what damping is. So that is what happens when we introduce R into our circuit, right? When we introduce a resistor. So it gets complicated. It gets complicated. So this may seem like a second lecture, and that's okay. I think this is very important to go over. This will help you a lot for the last couple of problems. So this is for no damping. No damping. Very bad. Damping is very bad here. Okay, so now what happens when we include damping? What happens when we include damping? Well, this is what happens when we include damping. So now we have R, L, and C all in series with one another. This is an RLC series circuit. If we want to look at how the charge changes with time, right? So once again, or no, actually we don't look at charge just yet. We want to look at the energy of this. So we now have differing amounts of energy. We have UL plus UC plus UR. I believe that's how we do this. I did this last night in a daze post-election mishap, so forgive me. I need just a quick moment just to make sure that what I'm writing is correct and not absolute garbage. Okay. Where are you? Okay. LC oscillator, RLC oscillator. Li squared R dq dt minus Q over C. Oh, okay. So when you're looking at an RLC circuit, it's really easy to apply Kirchhoff's loop rule here. So pick any point and then go around and calculate the change in voltages. So if I go down, I have minus Q over C, right? That's the voltage drop across the capacitor. And then I have minus IR across the resistor. And then I have minus L d I over dt. And this is all equal to 0. So we see here, since they're all minus signs, I can just drop the minus sign. Just give it all a plus sign. Essentially, I moved it over to the other side. And now I have an expression that I can work with, right? So I have Q over C plus dQ over dt R plus L d squared Q over dt squared is equal to 0. So now we're once again going to have a differential equation, but it's going to be a little more complicated this time because now there's a damping term. I'm sure that none of you, unless some of you have taken a differential equations class, I'm not sure if any of you have, this is going to seem brand new, and I'm going to show you how to actually solve this type of problem, because the way that it comes up in the textbook, it's a little confusing. It just tells you what it is. I don't want to do that to you guys. I want to actually show you for the first time where this thing actually comes from. So we have d squared q over dt squared plus dq over dt, and this is R over L. I'm basically dividing everything here, is equal to minus Q over L C. So once again, I have d squared Q over dt squared plus R over L dq over dt is equal to minus omega naught squared Q. And once again, we called omega naught 1 over square root of L C. So now we have a differential equation here. How do we solve this? How to solve. Well, so you can't integrate exactly. You need to know a lot of, how would I describe it? So in order to integrate, you'd need to know a lot about the initial conditions of this. So all I know right now is that the initial charge is probably Q naught, right? But I don't know anything else right now. So in order to solve this kind of problem, there's a method in differential equations called using an ansatz. And using an ansatz means, okay, I'm going to assume that my solution is going to be of a certain form. It's going to look like this type of function. And then I'm going to throw it into this differential equation and try and get some of those constants out. So I'll show you what I mean. So let's assume for a second that Q of t is equal to Q naught. So you can use sines and cosines. Do I want to use sines and cosines? I'm going to use complex exponentials here, just because I feel very comfortable working in that. And at the you should you should at least see how complex exponentials work. So this is e to the I omega t. So I don't know if you've seen it already, but e to the I omega t, right, is essentially, cosine omega t plus I sine omega t. Right, it's just sines and cosines. It's just representing it in a different form. Right, this is Euler's identity here. Okay, so now let's throw this into the differential equation. Well, d squared q over dt squared is just equal to minus, so I'll do one at a time to show you. So this is d over dt, dq over dt, which is equal to d over dt. I'll do minus here, minus I omega q naught e to the minus I omega t. And this is equal to now minus omega squared, because we bring down another power of I omega, q naught e to the minus I omega t. This is why we like to use it. It's really powerful in this sense. It's just minus omega squared multiplied by the original function you had. Who would have thought? So we don't know what this omega is. This is different from omega naught, which I wrote down earlier. This omega is some other omega. We're trying to figure out what this constant is. That is how this entire technique works. You essentially assume a form with some constants, and then you try and solve backwards to figure out what those constants would be to satisfy this equation. So now we see dq dt is equal to minus I omega q of t, and q of t is still q of t. So if I plug it into the differential equation above, I get minus omega squared q plus r over L minus I omega q is equal to minus omega naught squared q. So, oh, hey, look at that. That is why I chose this in the beginning. When I used to see this, I used to always wonder, why is the function that we choose something weird like sines and cosines or complex exponentials? This is exactly why. It's because it disappears at the end. Which I are you referring to? I'm not sure which I to which you're referring. So in this case, right, that's what I thought you meant. So we're going here, right? So dq dt brings down 1 power of minus I omega. If I take the derivative again, I bring down another power of minus I omega. And so I'm left with I squared, right? And that's just equal to -1. So the imaginary unit disappears when you take a second derivative, and you're just left with a -1. You're just left with a -1. It disappears entirely. Yeah. So this is why electrical engineers tend to use J for the imaginary unit, because they write a little I and refer to that as current. So I'll say here for this problem, I is equal to the square root of -1. So just to avoid any confusion, that is what I is here. Okay, so now we're left with another equation, minus omega squared plus r over L, or really minus is equal to minus omega naught squared. So if putting it all together, I have omega squared plus I r over L omega minus omega naught squared is equal to 0. And so what is this guy? The only way I can solve it is via the quadratic formula. So the quadratic formula tells us, x is equal to minus b plus or minus b squared b squared minus 4ac all over 2a. You know, I'm not going to derive that. That's will take me another 20 minutes, which we don't have. So this omega is equal to minus b, right? So this is b. This is c. And that's a, just so that we remember, right? So omega is equal to minus b, so this is minus IR over L, plus or minus b squared. So b squared is minus R squared over L squared, and minus 4ac. So a is 1, c is negative omega naught squared. So this is plus omega naught squared, plus 4 omega naught squared, all over 2a, which is just 2. Simple enough so far. Okay, so this is equal to minus IR over 2L plus or minus 1/2 square root of 4 omega naught squared minus R squared over L squared. And this piece right here, I can take out the 4. I want to take out the 4 here. So this is equal to this mess plus or minus 1/2 4 omega naught squared minus R squared over 4L squared. So it gives me a 2, and then that cancels out with the 1/2 here. So this gives me minus IR over 2L plus or minus square root of omega naught squared minus R over 2L squared. And I wrote that strategically because it looks the same as though it's on the outside. So now I can call that something new. I can call R over 2L. I'll call it something else. I'll call it omega prime. Call it omega prime. So now, finally, I have this new omega is equal to minus IR, minus I omega prime plus or minus square root of omega naught squared minus omega prime squared. So this whole frequency of oscillation is going to have some oscillatory term and some damping term. So this is our damping term here, and this is our oscillatory term. And I'll show you what that means. So plugging it back into the beginning, right? We see that Q of t is Q naught e to the minus I omega t. But we know what omega is, so now we can figure this out. This is Q naught e to the minus. So let's plug in the first term. Minus I, and then this first term gives me minus omega prime t. And then this other term is e to the minus I squared minus omega prime squared t. So what does this mean? What does this mean? This means that if I were to plot this, right, as a function of t and Q of t, we know that originally it starts at Q naught. And here's minus Q naught. What's going to happen is this term here will oscillate forever, but this is just an exponential decay. So what you're going to get is something like this. It's going to decay on both sides. And that's what happens when you introduce a resistor, because some of that energy gets sapped off with every oscillation until eventually it goes to 0. And so you can figure out now for an RLC circuit, the resonant frequency of that circuit is equal to this whole mess, right? Is equal to minus I omega prime plus or minus square root of omega naught squared minus omega prime squared. That's it. And this is actually written in the textbook. So this is for section 31, 2. And it shows these oscillations. And so if you have a pure LC circuit, you can figure out the resonant frequency of that LC circuit, right? It's just 1 over square root of LC. But if you want to actually use an RLC circuit, you're going to have a different resonant frequency. It's going to change. You're going to be looking at ratios. So really quick, problem number 9 sort of illustrates this. Problem number 9 says, what resistance R should be connected in series with an inductor and a capacitor? So they have some values for the maximum charge in the capacitor to decay to 95%. So we need to figure out, okay, at what time is it going to decay to 95%? And we need to assume, we're also assuming, so this happens in 70 cycles. And we can assume that since the damping is small, in that expression that I wrote before, you can assume that omega prime is approximately equal to omega in this case. I believe, it's equal to, sorry. They wrote it a little differently. So they assume that since the damping is small, you assume that omega is approximately equal to omega naught, approximately. Okay, so what you would do here is you can write, you need to know that the period of oscillation is 2 pi over omega. And so you can figure out what this omega should be because you know the value of omega naught, right? So this is 1 over LC. So you can figure out the period of oscillation. So you can find the time for 70 cycles. It'll give you some, you'll find some T naught. And then you can remember that Q falls like e to the minus omega prime T. It starts to decay like that. So now you know what this omega prime is. This is R over 2L. So using all of this information, you can now figure out, okay, what does R have to be in order to make this work, right? So this is T70. No. So you know that 0.95 Q max is equal to 0.95 e to the minus R over 2L T70. And so everything else you can plug in, but the only thing you need to figure out at that point is just what is the resistance need to be in order to make this work. I know it was a little rushed at the end. I know you have lecture right now. I will upload this and I will upload this and I will have this for you guys so that you could submit it, the homework for Friday, okay? If you have any questions, please email me. I'll be available to try and help you with your homework problems, okay? Thank you. Thanks for coming to my TED Talk. Please try and take it easy. I know you have lecture in a couple minutes, and I will see you next week. Bye, everybody.